Okay, so this last video file is going to show the last two questions from our first homework assignment 7-1. So we'll look at questions 11 and 12. Question 11, obviously a lot of stuff involved here, but you take your time with it. Hopefully the first two parts in particular aren't too bad, but there are a few stages that are kind of tricky, so obviously I'll work through this one as well. So in the figure below, point P is on the rim of the wheel, radius 2 meters. At a time of t equals 0, the wheel is at rest, so we know our initial velocity should we need it. And point P is on the x-axis. The wheel undergoes a uniform counterclockwise angular acceleration of 0.010 radians per second squared about the center. Okay, so they give us our constant acceleration, which is good to know, so we know our alpha. Part A, at time t is at 0, what is the initial tangential acceleration? So really, I threw an initial there. What this question is looking for is really right at the instant that this object starts to spin. What is its tangential acceleration? Well, at time t sub 0, it does still have this angular acceleration. Okay, so for part A, the question is, how do I find the tangential acceleration? And notice this doesn't ask for the total linear acceleration. That actually comes up later. Part A is just asking for the tangential acceleration. Okay, so the tangential acceleration is the one of our two linear accelerations that relates to the angular one. Okay, and it relates to it the same way that we've seen some of the other linear measurements relate. The tangential acceleration equals my radius times my angular acceleration. Okay, so part A is actually, once you realize what the question is asking for, and obviously if you're comfortable with the relationship, it's pretty straightforward. It's plugging in the numbers that we know. Okay, so they give us the radius of 2 meters, and they give us the angular acceleration of 0.01. So then I know my tangential acceleration would be 0.02, right? Just multiplying 0.01 times 2. Okay, so there's my, and excuse me, it's not radians per second squared, it's now meters per second squared. Okay. So there's my tangential acceleration. Okay, so nothing too tricky, hopefully, about that first part, as long as we know what the question is asking for. And that maybe is the toughest part. Okay. Part B, what is the linear speed of P when it reaches the y-axis? So we want to find what the linear speed is. So we want to find our v once the point has rotated up to that point up there on the y-axis. Okay, so we're looking for v. And again, with a problem like this, the easiest way to find v is to think about how does it relate to my angular measurements. We know that v relates to w, right? We know that v equals r times w. And since we obviously still know the radius, the real goal of this question becomes, can I find my angular velocity at that point up there? Because if I can find my angular velocity, there's not really any calculation involved, right, to finding our velocity. Okay, so we want to find our angular velocity, so we're looking for our final angular velocity at that point. We know our initial angular velocity because the object starts at rest is 0. We know our alpha, our angular acceleration, is 0.01. So then the question is, what other measurement do we know? Do we know anything about the time, or do we know anything about the angle? Well, if you look at your theta, we definitely know the angle measurement, right? From the time that point P is on the x-axis to the time that it's rotated up here, that's rotation of 90 degrees, but again, the important thing, we need to make sure we're thinking in terms of radians for theta. Okay, so whether you have to convert, most of us probably don't have to convert it. Most of us have already used the unit circle enough to know that that is just a measurement of pi over 2. Okay, but if you did have to convert, you could just convert 90 degrees to radians by doing 90 times 2 pi over 360, and that would also take you to pi over 2. Okay, so we've got our third measurement that we need. So we now have our theta, we've got our initial angular velocity, we have our acceleration. So we can pretty easily find, using kinematics, our final angular velocity, and then obviously plug that in to find our linear velocity. Okay, so probably using this formula, unless you want to do 2 steps out of it, we can set up the final velocity equals the initial squared, the final velocity squared equals the initial squared, plus 2 alpha theta. Again, plugging in the measurements we know, we're looking for the final velocity squared. This is 0 plus 2 times my angular acceleration of 0.01. Whoops, I don't know what happened there. And then times my theta measurement of pi over 2. Okay. So plugging in those numbers, do notice I use a 0.01, my angular acceleration, and not my linear acceleration. But otherwise now it's just solving the rest away for my final angular velocity. Okay, so when I do that, yada yada yada, I should get that to be about 0.177 radians per second. Okay. So then finding my velocity, my linear velocity, it's just my radius of 2 times my angular velocity. So I get 0.354. And that is meters per second. Okay, so 0.354, I know that's tough to read, but you guys should be used to my handwriting by now anyway. Okay, so 0.354 meters per second. So part C and D. Okay, part C and D kind of just extend on this a little bit more. What is the magnitude of part C is maybe the trickiest part because it does come back to what is the net linear acceleration. Okay, so the tricky part there is we do have to be comfortable with the fact that the net linear acceleration is not just the tangential acceleration, right? There's two forms of it. There's two forms that can bring us linear acceleration. So again, reviewing this, if you look through all of these, you've seen this before, but the linear acceleration comes from both our tangential, which we already know to be 0.02 meters per second squared, but we also, if we're moving in a circle, we always have centripetal acceleration, and centripetal acceleration is a form of linear acceleration. I know it doesn't always maybe feel that way, but it is a form. It is just a vector in that sense. Okay, so we still need to find our centripetal acceleration. Good news is we just found our linear velocity. Okay, so plugging this in is actually just a simple calculation. 0.354 squared divided by our radius of, again, 2 meters. We should get our centripetal acceleration to be 0.0627 or thereabouts, right? So now we know our centripetal acceleration, we know our tangential acceleration. If we're thinking about at point P up here, the tangential acceleration would be going off, obviously tangent to the circle. The centripetal acceleration is going down. So if I want to find my net result, and the good news is it does say in the question, we're just looking for the magnitude, so I don't have to mess with the angle, right? I don't need to find any angles involved. But if I want to find my magnitude, I am going to have to do the Pythagorean theorem. Okay, so my total linear acceleration is going to equal the square root of my tangential acceleration squared plus my centripetal acceleration squared. Okay, so at this point, it's just a matter of plugging it in and calculating. Okay, so when I do that, when I plug in my 0.02 squared plus my 0.0627 squared, I get something that comes out to be about 0.066 meters per second squared. So again, find total linear acceleration. Maybe one of the trickiest kind of concepts in this first one. Total linear acceleration comes from both the tangent and the centripetal acceleration. And then finally, part D. Part D asks us, how long after starting does it take for P to return to its original position on the x-axis? Well, we're looking for the total time that it takes to make one revolution, right? So we are just going to come back to linear kinematics. We're looking for part D, the total amount of time that it takes to make one revolution. Well, we know that one revolution is 2 pi radians, and that's one of the big inclusions here. Otherwise, we know our initial angular velocity is 0, and we know our acceleration is a constant 0.01. Okay, so this really then just comes down again to angular kinematics. We've got 3 of our 4 measurements, just find the 4th. Okay, so probably most of us reference this equation here, since it does simplify pretty nicely, right? Since our initial angular velocity is 0, then we just have to mess with our 1/2 at squared. Okay, so my theta equals 1/2 0.01 times t squared, and again I know my theta is 2 pi. So then solving for t, I get that to be about 35.4 seconds. So anyway, probably trickiest parts on this were B and C, I think, for most of us. B because it's a little bit less ambiguous in terms of where to go, although as long as you can break up the angle for part B, not too bad. And then part C, again, understanding what it actually means to be the total linear acceleration, right? If it was moving at a constant, If it was moving at a constant angular acceleration, we'd be able to eliminate this, but you can never eliminate the centripetal acceleration if it's moving in a circle. Okay, so just make sure we're careful with that. And then finally, the last question. We've got meathead Roblo. I typically tend to prefer the one that's critiquing his neighbors on building the shed, but we'll go with the meathead Roblo anyway. Okay. So at a local swimming hole, a favorite trick is to run horizontally off a cliff 8.3 meters above the water. So we've got our cliff. It's a jagged cliff. That's okay. I know that the height is 8.3, and I want to run off this way with a velocity. Okay, so I just want to run off the cliff. I don't want to jump up. That would change things a little bit. Okay. Meathead Roblo, being a bit of a show-off, decides he wants to tuck in a ball and see how many times he can spin on the way down. So he rotates on the way down with an average angular speed, which is my W, right? It's my angular velocity of 1.6. Notice it is revolutions per second. Now you could convert that to radians, but in this case it asks us how many revolutions does he make, so I can actually leave this in revolutions, and here's why. This is his average. If this is his constant angular velocity, then the only thing I need to do is angular velocity equals theta over time, right? So if I want to find out how many revolutions he makes, I need to find out how long it took him. Well, I know his angular velocity. I'm looking for the time. I can take a step back and just go to good old kinematics that we know from way back in the second and third chapter of the year, right? We know that if he runs off the cliff, his initial vertical velocity is just 0. The acceleration as he falls down towards the water is our 9.8. It's our acceleration due to gravity. And we know that the height, so it's delta y, delta x, however you want to think about that, is 8.3 meters. Okay, so really, I've got those three kinematics measurements. I can use those to find the time that it's going to take him to hit the water below, and then just plug that time in over here. Okay, so this question's tricky because it's one of the questions that relates linear measurements to angular measurements. And I know until we get comfortable with these type of relationships, it is going to be a tough problem. It's something you just have to kind of get used to, and obviously that comes through more and more practice. Okay, but in this case, I just use my delta x equals 1/2 at squared to find my time. So 8.3 equals 1/2 9.8 times t squared. T then would equal 1.3 seconds when I calculate that. Okay, so there's my time. And again, now that I know that, I can plug that in over here. So I've got 1.6 equals theta over 1.3, and I can solve for theta, which I find to be about 2.08 revolutions. And since the question did ask for revolutions, I don't have to worry about converting revolutions to radians or anything like that. I could have and then converted right back, but obviously that's an unnecessary step. Okay, so anyway, this finishes out our first homework assignment. I'm sure you guys have all watched each and every one of these videos rigorously, but hopefully it does help. If you do have questions, obviously let me know, but hopefully this can help you work through some of the more challenging homework questions as well. So anyway,